Okay, good morning, afternoon, or evening, everybody. Welcome to the Introduction to NASA's GEO-LEO Dark Target Aerosol Data Products Earthdata webinar. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Daylight Saving Time, so we're going to go ahead and get started. What I'll do first is begin today's event with just a few logistics. To ensure the best audio experience, all participants have been placed in silent mode, but if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A panel rather than the chat, and you should find that located on the right side of your screen. If you do not see the Q&A panel, click on the three dots in the bottom right side of your screen, and that will open up your panel options, and then you can insert a check mark next to the Q&A panel. Today's webinar is being recorded. The recording will be posted both to the NASA Earthdata website as well as to our NASA Earthdata YouTube channel within a week of completion. And then once completed, what I will do is I'll send an email to all registrants, excuse me, with both the recording links and the presentation slide deck link used within today's event. The presentation, as far as timing is concerned, today's webinar will be 1 hour and 15 minutes long, and we will allocate 45 minutes to the presentation and live demonstrations. A 15-minute Q&A period will follow, and depending on the volume of questions that we receive, we may extend the Q&A session an additional 15 minutes from end time, but we will have a hard cutoff of 3:15 p.m. During this afternoon's webinar event, we will have two speakers. At this point, I'm going to actually advance to the agenda. Our first speaker is Dr. Robert Levy. Dr. Robert Levy is a research physical scientist and also principal investigator within the Climate and Radiation Laboratory at Goddard Space Flight Center. He will begin today's event by providing an introduction to aerosol measurements and why we care about these measurements, and transition to an introduction to the GEO-LEO Dark Target Aerosol product suite. He will cover both level 2 and level 3 data sets. And then from there, we will transition to our second speaker for this afternoon, Tassia Owen. Tassia is an outreach coordinator at NASA's Level 1 and Atmosphere Archive and Distribution System, Distributed Active Archive Center, or LAADS DAAC, and that is also located at Goddard Space Flight Center. She will provide a demonstration for how to discover and access these new GEO-LEO Dark Target Aerosol products using NASA's Earthdata search. After Tassia has finished with her demonstration, what we'll do then is we'll transition to another optional final set of polling questions and then just jump directly into the question and answer period. Before I toss it over to Dr. Levy, let's cover just a couple of notes regarding the Q&A. We will try to answer all questions within the time allotted, but if we're not able to address your question during the Q&A period, our speakers will be able to follow up with you offline. With that, I am going to stop sharing my screen, and it is my pleasure to introduce our first speaker this afternoon, Dr. Robert Levy. All right, so let me stop sharing my screen here. And I am going to toss the presenter role over to Robert. All right, so you should have presenter role at this point.
I think so. So I think you can see me. I'm sitting in my office. So I'm Rob Levy. And I guess I will start in the presentation. And I do want to mention there's a few group members here. So if they want to show themselves, they can do that too. We have I see Jennifer, Mijin, and Virginia online, and some of them may have other folks in their offices that are part of our group as well. So they'll be here as panelists to answer questions if needed as well. So let me start on the presentation. I'm sharing my screen and making this thing, and I guess I should start at the beginning, right? Not at the middle. So we'll start at the beginning, and hopefully I'm in presentation mode. Is that right? Can you guys see this?
Yes, you are.
Okay, excellent. So I'm talking about the introduction to our GEO-LEO Dark Target Aerosol data products. And I added here just a link, and I think you said they're sharing slides later on, so we can, this is to our website, that's our group's website that has more information about the algorithm and how it's used in many places. So let me just mention that there's a lot of contributions here. These are some pictures from recent Teams meetings. I guess I cannot tell who, if people can show faces and such, but we have folks from our lab here. So that's Shauna Matu, Yingxi, Virginia, Praju, and Mijin. And I think some of them are online. We have folks from the Terrestrial Information Lab who've been helping us develop and produce and provide and share these products. So those include Bhaskar and Jennifer and Xiaohui as others. Folks in the Biospheric Lab, that includes Pawan Gupta. From the University of Maryland, we have Lorraine Reamer. Wisconsin, we have Min Yu and Bob Holtz. Early on, we had some work done and help from folks at NOAA, including Shoba and Hai. And we've had some help from interns as well. So that's Sally and Neil. And so, a lot of folks have helped to get this going and to get it produced into a product. Yeah, so let me just tell a little science background of what we're after here. This is basically a picture. I'm not sure I originally actually got it from, so I guess I should reference it someday. But it's basically different kinds of aerosols or particles in solid or liquid suspended in our atmosphere. And they come from natural sources such as dust, sea salt, and volcanoes. But they also come from man-made sources such as auto and power plants. And forest fires and crop burning are also big contributors as well. And so just the idea of this picture here is just showing different sizes and shapes of the different kinds of particles. And we tend to live in a world we call the fine size and like smaller coarse particles. So in the order of 0.1 to 1 micron or so, plus or minus partial orders there. And what's interesting is that those aerosols of these size and shapes also have the largest impacts on radiation. So on radiative budgets, of reflecting sunlight, visibility, also cloud processes, and they also contribute and can be detrimental to our health. So those are different reasons why we study aerosols. And to add on as well, why do we care? As I mentioned, affecting visibility, health, precipitation, chemistry, biology, the list goes on and on. They're kind of everywhere. But they're very inhomogeneous in space and time, and their distributions are changing and sometimes very rapidly. So it's a very interdisciplinary subject working on aerosols. And for that, we are looking for data sets that characterize climatology, trends, and variability. And so this is a model of aerosols around the world. So this is from Goddard's in-house model called GEOS-5. And what we see here is kind of an animation of different types of particles floating around the Earth. So we have dust in the orange, organics in the greens, sulfates in the whites, and sea salts in the blues. And you can see this, how rapidly they can move, and they follow the weather fairly well. And then they have, major sources as well. And so, and then as I mentioned, they impacted by air quality. And so if we have better modeling, forecasting, and assimilation, then that can help. And so this is back to the model. This is all a model, and how much of this can we actually observe is our question. And so to answer some of that, we can see aerosols from space. So these are early pictures from MODIS. MODIS was a moderate resolution imaging spectrometer, and that was launched early in late 1999 with its first observations in 2000. And these are some early observations of haze over the Bay of Bengal and smoke from Canada into the US. And they're on all over Earth Observatory website, many examples like this, just showing how well we can see these particles from space. But we're trying to quantify these particles. And so the property that we're trying to measure is called, one of them that we're measuring here is called aerosol optical depth, which is related to the quantity of light removed by a beam by scattering and absorption during its path through the atmosphere. And so the aerosol portion is aerosol optical depth, and many of us would commonly report in a mid-visible wavelength, such as the green, such as 0.55 microns or micrometers. So AOD can be measured directly from the surface using something called a sun-photometer, where the ground reflectance is negligible, and we can pretty much measure exactly what the optical depth is. Or it can be estimated from a passive sensor on a satellite, but you do have to take into account the ground reflectance as well as observing you really only can see the light scattered portion. So, but you have to note that optical depth represents the entire atmosphere and not just the nose level that is at, that might be important for air quality and such. But we're, for many reasons, we're still attempting to measure aerosol optical depth. So what the dark target algorithm is trying to provide is how it's doing this is it relies on surfaces or targets that are dark. And you can see from these pictures, which offer a contrast to the particles above them. The open ocean is dark in certain near infrared wavelengths and long visible, and dense dark vegetation is dark in some visible and shortwave infrared wavelengths. So we use that to see the contrast of the particles. And unfortunately, the dark target algorithm is not meant for working over deserts or ice snow. And there are definitely other algorithms and products that are more appropriate for this. So in theory, we can all work together and produce kind of global products that are even better. But the dark target requires clear skies, so no clouds, and also be far from sun glint. And it doesn't work at night. But this is the basis of this relatively simple algorithm that we've been using for a long time, led by Yoram Koft and Didier Tonray. So that's over 20 years ago, almost 30 years ago, they've developed this algorithm. So just, showing it another way, our algorithm must account for many factors. So we just see a picture of the sun and the satellite, and there's all kinds of things in the way, including the aerosols that we're trying to find. So we have to make assumptions about the surface and the Rayleigh, the molecular part, gases, and 3D reflective processes. Anyways, to do all that, we have our magic algorithm. And so I have an example from early on from MODIS. And you see on the left is like a picture, a red, green, blue image, what we see with our eyes kind of visually, using our fancy algorithm called dark target, using multispectral observations in as well as long wave, as short wave infrared. And we get something on the right that's aerosol optical depth. And you can see semi-continuity over land and ocean. You can see where we don't retrieve over glint or clouds. But you get a pretty good handle on, and now take this one instance and start aggregating it over the globe. And this algorithm has been improved multiple times, as I mentioned here on the right. So just, one summary here of, things we've learned. We've learned a lot of things from MODIS. It's very, very well used and, referenced data sets. But really what we've learned a lot about the daytime view of the global aerosol system. From dark target only, it's minus the deserts and poles, and you get a sense of seasonal averages. On the bottom here we have a long time series, so it's been since over 20 years, almost 25 years from MODIS on Terra. And we have these two sensors, each with stable orbits, excellent calibration. And there are some small differences that you can see, but they're well within expected uncertainties. And so just mention here that these MODIS products have been long time hosted at LAADS. And we also produce a level 3 product, which is taking these level 2, these individual retrievals and aggregating them up to a daily and monthly time period. And so one thing I wanted to mention is that, those are individual cases, and we have the Global Climate Observing System, who's come up with requirements for optical depth. And for a long-term and wide data record, what they call a climate data record, they make these recommendations for what kind of things we're after. So for MODIS, we get things like pretty decent horizontal resolution, pretty good accuracy, pretty good stability bias over the long term. It takes a lot of work to do that, but we're almost to that point. But with MODIS possibly ending or likely ending in the next couple of years, we're not going to get to the recommended time length. So there we look to other sensors. But more importantly, we don't have the temporal resolution from the MODIS only, because we really only get once a day, maybe twice a day. So we really want to improve both of those and get a larger record. So the extension of our long-term record, or our dark target, is using VIIRS. So it's the visible and near infrared radiometer suite. And it was first launched in SUMI NPP, another satellite, in 2011. And additional VIIRS sensors are also on NOAA 20 and NOAA 21 currently, and will be launched later in the next couple of years on the rest of the NOAA's JPS series. So between MODIS and VIIRS, we should satisfy the multi-decadal record. But however, porting the algorithm required dealing with things like wavelength shifts and spatial resolution differences. And so to that, we have MODIS dark target products, as well as VIIRS dark target products that are hosted by the LAADS DAAC. And notice I just mentioned one's called Modo4 and one called XAERDT. Those are their names in the records, in the databases. And you can see from the middle pictures that, you can't really see any visual difference between MODIS and VIIRS. Two different sensors, but the algorithm's reported. So we know we can do that. So with Terra, Aqua, NPP, and the NOAA satellites, they're all in something called Sun-synchronous polar low Earth orbit, or LEO. And so basically, from each of these sensors, we see the Earth once a day. But we don't think that's good enough for these requirements. First of all, there's places in the globe, and this is from an old paper, where aerosols may change on average throughout the day. So this is Mexico City, and you can see where the two MODISes were, Terra and Aqua. Even that's got some time differences, but over the course of the day, optical depth and spectral dependence of the optical depth, called angstrom exponent, can change rapidly. And so we want to learn how to understand that. At the same point on the right here, with our from the geostationary world, which I'll describe in the next slide, we can see how this is Canadian smoke can change rapidly and how it moves. This is only like a day's worth of, not even a couple hours worth of observations. And you can watch these heavy smoke moving. And so we want to learn how to combine and take this into account. And so just some more examples on what is a low Earth orbit. That's on the left. And you can see how it takes once a day to cover the globe. And on the right, we have a geostationary where it's looking at one place, but the sunlight is changing underneath it, so you see throughout the day. And so these images are from animations from ARSET. ARSET's a group or part of the applied sciences doing training on how to use remote sensing. And so with these geostationary imagers, we actually have quite a few of them. So about basically now we have ABI on, so something called Advanced Baseline Imager on GOES East and GOES West, the US satellites. There's a European one that was launched last year and is soon will give us data that we can use. It's flexible combined imager over Europe. And then there's AMI and AHI Korean and Japanese instruments. And they are, so you get kind of a sense of a geo ring. At the same point, if we compare MODIS and VIIRS, these are wavelengths and spatial resolutions. And for many, there are some missing channels in the AHI and ABI, but for the most part, most of the bands that we're used to, wavelengths we're used to for MODIS and VIIRS, are also on the Himawari and Advanced Baseline Imagers, and they're at somewhat similar resolutions. So we felt like we could go ahead and try and do our same dark target retrieval with some modifications and do it on the GEOs. And so this was our first attempt from a case in 2017. So this is before the NOAA GOES satellites were considered operational. But we went ahead and did this retrieval, and we watched Canadian smoke move across the US, as well as some smoke over Brazil. And we were kind of satisfied, thinking, okay, we can go ahead and do this. And so we went and said, we asked the question, can we apply the same dark target algorithm in a consistent way? And maybe can we combine this into a single product that thereby gives you more of the globe and more time coverage as well? And so that was what we had in 2017. We had ABI on GOES West, we had ABI on GOES East, we had Himawari. This is places we had access to the data for. And then we had the two MODIS, Terra Aqua, and we had VIIRS and BP. You can see, again, there's no coverage over Europe for the GEOs, but we have some coverage over the rest of the globe. So we said, hey, can we do this? Can we add high temporal resolution to the global long-term aerosol record, and create a synergy of LEO and GEO? And so this is a proposal we wrote to making Earthdata records useful. The name is longer, but the acronym is MEASURES. And so we went ahead and said we want to develop a level 2 product, which is consistently applying the dark target retrieval on all the sensors, and also make it consistent so we don't have differences how this data look. We want to have the same use and feel to all the different data, all the different products. We want to make a merge for level 3, which is create a gridding system and infrastructure to ingest and create a single product on all of them. And then, of course, this purpose of this seminar is to show how we're archiving this data, where it lives, and communicating what it is and what we want. And hopefully we haven't had much chance to do it yet, but the goal is, of course, to do science, to answer science questions about aerosol transport and variability. So that's what we've been after here. So now I'm going to go into some examples of what we did and what we have there. So this is a case study it was pretty well known, these Australia fires in early 2020. And they were interesting because the fire was so intense that it sent smoke across from Australia into South America. So this is one of our data of taking multiple granules. So that's the level 2 data. So this is the LEO, the low Earth orbit. So we have 2 timestamps from Terra, from MODIS on Terra. We actually have 1 timestamp here from Aqua, but it's kind of near the poles, so you don't really see it here. And then again, these are daylight, so there's some daylight in some of these granules. So nighttime, we don't have data. We don't do data at night. And we have 2 timestamps from NPP, from VIIRS. And we actually have 3 timestamps from the GEO, so they run every 10 minutes. So it's this Himawari 8 over Japan, goes west over the middle of the Pacific, and goes east, that is centered here east of South America. And so, yeah, one sensor at one time doesn't give you very much, but you can see how, we can start aggregating things together. So we're using the same exact, as close as possible. I don't want to say exact, but as close as possible. The retrievals are similar for every sensor. We're denoting this product as XAERDT, which is to indicate divergence from what we've done with MODIS in the past and what we've done with VIIRS in the past, so that this is its own retrieval that might be slightly different than the traditional MODIS or VIIRS standard products. As we'll see, the reported variables are the same for each sensor, and all files are in the same format. So that's what we did from the level 2. And our intention for level 3, and we do have a couple bugs still in here, so that's why we don't have data available yet for level 3. But the idea is that you take, well, again, each of the level 1s, which are the individual reflectances from each sensor separately. We do our retrievals for each sensor separately, so we have all the LEOs and all the GEOs. And then we're taking some quality filtering. So each of these, I didn't mention it, but all the individual level 2 retrievals, the individual along orbits, have different diagnostics and quality assurance and such. And so we're going to take all that information and use that quality filtering and basically create everything on a 1/4 degree by 1/4 degree and 30-minute time intervals, so that we have statistics of the individual sensors as well as merge statistics. And for certain variables, we'll have the mean, the standard deviation, the number of pixels or retrievals that went into it, and in case of the merged, the number of sensors at a particular timestamp that went into it. And so we're going to report the optical depth, a couple different versions of it, as well as the geometry. So that's what our plan was for level 2, level 3. And so here's one example. And you can see, if you remember the level 2, the level 3s look pretty much identical because they're just on 1/4 degree by 1/4 degree grids. But these are gridded now. And here's a joint product. So this is the merged GEO-LEO on top of essentially a red, green, blue picture, which we had fun making, where we used Himawari from the Australia area, goes west and then goes east. And so we can tie together the visible image at one timestamp here. So it's everything that happened between 2100 and 2129. So at that time, so everything gets combined to this merged GEO-LEO here. And what's kind of fun that we can do, and we haven't really started doing it yet too much, but for every timestamp now, we can then compare it with things like models, reanalysis. So this is a reanalysis product from ERA, which is here at Goddard. But the MERA, the reanalysis, doesn't use the geostationary retrievals. It uses other information for its reanalysis. And so now we can compare our GEO-LEO merge along with the reanalysis, and you can get an idea of what's going on at every timestamp. At least that's our intention. So here's our product. We call it XAERDT. It uses a similar algorithm we call the dark target package. And we don't go into details here, but we had to do this. To make this work, we had to produce it on many different machines. So it's not all done in-house at Goddard. We did some of it at University of Wisconsin. We've aggregated and used a whole bunch of different resources to try and but yet consistently create the level 2s. So this is 6 sensors that we worked this on. So we have MODIS Terra, MODIS Aqua, VIIRS on SUMI NPP, the 2 ABIs, the Himawaris. And it's interesting because Himawari, we planned to do this from 2019 to 2022, and the operational Himawari instrument through the 13th of December of 2022 was Himawari 08. And then later in the month, they converted to 09. So in the data product, you'll see 08 up to a certain point and then 09 afterward. And then the level 3, which is, of course, still almost done, but it's not quite there yet, which will be quarter degree and global degree in half an hour. And so now we'll get into some of the data itself. We'll go over a little bit with the actual getting the data, but this is just the entrance page to the GEO-LEO dark target aerosol products. And just showing, I made, just did this on my own with clicking along. And I was like, I'm interested in the same image that I just shared, which is January 5th, 2020. And I'm looking for in this case, I was looking at the goes west data. So I have 2020. I go to day 05. And I scroll down and I find the image that I was looking for, the 2100 ABI Go 17 image that has this date and timestamp. And we just go over what, if you looked at data files, what they mean: year, day, hour, month, the version number, which is 1 in this case, and then the date, which is processed. And they're all, as I said, NetCDF files. And just for fun, I decided to just show a couple screenshots of using a free NASA tool called Panoply. And so from Panoply, you can click on a file, and all the level 2 files, whether they're GEO or LEO, are going to look the same. They're all going to have geolocation information, which is a bunch of angles and the latitude and longitude. And they're all going to have geophysical data, which I'll go to the next page and I'll show you what some of that is. But I just show an example of solar zenith angle here. So just with the software, you can click on it and it creates an image of the solar zenith angle. And this is, as you can see, where it goes west is. And all the daytime ones are in the bluish color. So that's where daylight is. And nighttime is when the sun is below the horizon, or on the other side of the globe. And so those are nights. So we only, for this from ABI west, goes west, we only expect to see retrieval somewhere in the daylight area for this timestamp. And then, so this is the geophysical data, and there's a whole bunch of different parameters. And again, they're all the same for all the different level 2 products from all the sensors. And I just picked here optical depth, land, and ocean. So this is the one we call our primary one, which is quality assurance filtered. So we use, so we expect this to be a little higher confidence than some of the other retrievals, which is, for example, the image optical depth, which is not filtered by QA. So it might have more data, but it'd be less confident. And all these other variables relate to quality assurance, diagnostic, or derived quantities. And if you notice, these are all in this NetCDF platform. And so they actually have information called metadata about the data themselves, like what the valid values are, what the long name, giving you a little more description, etc. And then here's what a level 3 should look like, although you can see it's grayed out here. When you look at the data center, it's not actually there yet, but when it's soon, you'll be able to select things like, again, the same thing, by the year, by the day, and you'll get data that looks much like this with half hour, quarter degree, and the same thing, the year, month of the data acquisition, as well as the year, month, day of when it was produced. and they're all in NetCDF file format. And I just saw a thing pop up on my screen. Why not why not HDF? It's just over the years, NetCDF is the more modern format for doing this kind of work. And so most of our files will be in NetCDF. And then just a picture of what what couple of the variables that are in here. So we're only going to give optical depth and angles. So this is the aerosol optical depth, what we call the filtered QA, which is the number of sensors that went into this. And you could see that there are a few spots where there are actually 3 sets of data. 3 sensors gave observations at the exact same time, but others are only 2 or 1. And here's the merge retrieval for that case. And then finally, again, we calculate offline, but it's in the file. The day, what is the solar angles for the whole globe? And you can see where it's daylight and where it's nighttime, where we have a possibility of having a daytime retrieval. Anyway, so those were all the different slides that I had to share. I think next we'll have some demonstrations of how to actually get some data. I don't know if anybody I can't see who's on as panelist, but if anybody wants to share and say hello, I see Nijin and Praju and Virginia. Thank you for coming. And Min, thank you for coming. Min's from Wisconsin. So the rest of everybody else here is at Goddard. Jennifer. Thank you all for coming. And yeah, so I think they're going to stick around for asking questions too at the end. So yeah.
So thank you for bearing with me with technology. It has not been my friend today, and that just happens sometimes. So we are going to roll with it. So I'm Tasia Owen. I work in outreach and communications for the LAADS DAAC, which is the Level 1 in Atmosphere Archive and Distribution System, Distributed Active Archive Center, quite a mouthful. And we provide the data products that Rob just presented to all of you guys. So I'm going to show you a little bit on how to get to them. As I said before, I ended up having to take my walkthrough and turn it into a slide deck today. So we'll see how this works. Let's see. Let's move on to the next one. Come on. Well, oh, here we go. Okay, so in LAADS DAAC, there are 3 different ways that you can get to the data, which is this find data, view data, and LAADS archive that you can see up here in the data section. Additionally, you can get to that by clicking on either the view data or find data that's just here in that one bar on the bottom, that blue bar. Now, what we're going to show you next is how to get to the GEO-LEO products. So if you look on that far right side where it says applications and that orange button, and if you were to click on that orange button, you would then get to this GEO-LEO dark target aerosol card, which tells you a little bit about that. And if you click on that, you end up at the gateway page for the GEO-LEO dark target aerosol products. So here you can read all about the different products. So if you need to put a little blurb into a presentation, you can pull it from here. You can also learn about the aims and objectives. You can learn about the benefits, as well as look at the individual output products from this page, and also review any documentation. So on the output products page, you can see there's some drop-down menus in the different places where those different products are listed, as well as seeing what platform or sensor, resolution, both spatial and temporal, that are available as well. So if you were to click on any of those drop-down menus, you'd see that the product details are there, the order data or the direct download becomes an option to be able to access the different either the details of those different products or be able to actually get to the data. So if I were to click on product details, it brings me to the specific page for that particular product, which gives you a little bit of an overview. On the other tab, there's the product information, which goes over those things like that short name or that ESDT, as well as the naming convention, as well as some of the other very specific portions of that information. The other thing that you'll find under that drop-down menu is the order data. and under order data, it'll take you to our search and order interface, but it will also already have and the search and order interface is the same as find data. But here it already has that specific product populated for you because you pulled it directly from that one page. So you wouldn't be able to go and get all of the different data products listed at one fell swoop there. And I will show you how to get there in a little bit. And then next, we also have this direct download. In direct download, it takes you to that specific data product and into the individual year that those data products are listed. So if I were to go into, like, say 2020, whoops, this is how you use the archive. If I were to go into 2020, this is what I would find. And all of these numbers are the days of the year in the Julian calendar. And that just means that they're sequenced number 1 through 365 or 366 if it's a leap year, as far as the numbers are concerned. So if I was to say, look at January 5th of that year, that would be the 5th day of the year. And I would just click on that file, which would then open up all of the different data products that are available on that date using the VIIRS SNPP, which is the data product I chose to use out of this one. And if I were to scroll down, I could highlight either one or multiple data sets that I wanted, and then just click on the little download icon, which would actually allow me to directly download it to my computer. So that is how you would access it on the archive or the LAADS archive. Additionally, we have find data, which you can either pull from that data dropdown or click on this little green button that says find data. And this brings you to that search and order interface. And on here, you can see I don't have any products that are selected yet. But if I were to click on Aerosol, and then scroll down until I got to those XAERDT products, which are the GEO-LEO products that Rob talked about today, I could go in there and I can highlight the individual products that I want, up to 6 of them. That's the max number. And then I could have those 6 products selected, or a single product if you wanted to. And then click on the little arrow over here, this white arrow, which then brings me to time, or I can click on time as well. That'll do it. And I can either put in a date range or a single date. Here I've put in a single date of actually January 5th, 2020, which seems to be the one that we're using as our example. And if I click on add date, it adds my selection over here. And then I can click on the little white button, which then takes me to location. And here I have either world or countries, validation sites. I can draw a custom box, which here I drew a box around Australia because we were talking about the Australian bushfires. Or I can enter specific coordinates. For the purposes here, I'm just going to draw the custom box because I'm interested in aerosols over this particular region. And then click on the white button after I've entered that location. And then it will take a little bit of time. And actually, it'll generate all of those files that we saw in the archive. Here, you can either download the files directly, or you can click on the individual files that you want. So here I clicked on one for the 2200 hour of that day. And then review my order. And you can also click on the view delivery method. And here you can see that the method is the HTTP GET request. And then I just click on submit order, and it would take a little bit of time, but you'll be notified when your order is ready. This order would probably take a lot less time than, say, if I was ordering for multiple days or multiple weeks over all different locations. Next, the other method I wanted to show you, and I'm going to skip over, there was one more method on the LAADS website, which is that view data option, but currently GEO-LEO data cannot be viewed. Those granules are not available to be previewed on, on the server. So it seems like that wouldn't be the best use of getting that data at this time. So finally, Earthdata search, if you were to go to the search.earthdata.nasa.gov/search, you can look for a bunch of different data from multiple DAACs. If you were to click under organizations, you could actually search by LAADS DAAC, but for our purposes here, I know exactly what data sets I'm looking for, which are those XAERDT. So I could just enter that into the search bar up here, and it'll bring up the different data products. Currently, it's having an issue with the geolocation for the different granules with the geostationary satellites. So here you can see that they're only for those VIIRS or MODIS on those different satellites. Those particular data products are the ones that are available. So that is how you get it on, or get to those data products on Earthdata search. And if I go in, I can go to the different data product, and I can either add the collection to the current project by clicking on this little plus sign. I can remove it after if I did the wrong one. But if I actually just click on the whole product there, it'll take me to that particular product page where I can put in different search parameters, such as the different time periods that I would be looking for. So here, I previously entered these in, put in the January 1st, 2020, for between 2100 and 2200 hours. And that'll pull the data for that particular time. And then I can either select which ones I want, or I can download all of them from here. And that is how you can access these new data products, either from LAADS DAAC or from Earthdata search. So Jennifer, I am going to stop sharing, and I am going to pass it back to you. Thank you everyone for bearing with me on this.
Okay, well, thanks so much, Tassia. So let me open the final optional polls, and we'll just hop straight into the Q&A. There were actually quite a few questions asked in the chat, so I'm going to start there. You just give me a moment here. Let me, so I've got a little bit of space here. All right, let's see. If you have questions, it'd be great if you could type them into the Q&A. It's just a little bit easier to keep track of, and if somebody joins later, they're not cut off by, that chat that was asked much earlier within the event. Okay. All right. Okay, so the first question was, what kinds of human diseases can aerosols cause? Can animals also gain some of these aerosol diseases? Can you hear me?
Yeah, we can hear you, I think. I don't know if anybody in our group wants to try and answer that better than...
Do you want me to take this one?
Yeah, go for it.
Okay,
And introduce yourself while you're at it.
yeah, this is Lorraine Raymer. I'm part of the panel here with Yingxi. And it's a very good question. We know that particulate pollution, which is what these aerosols are, if you breathe them and they're the right size to go into your whole system, into your lungs, they can cause a variety of different health concerns, and different types of morbidity. It can be lung issues, it can be asthma, it can be heart disease, it can be many different things. And we highly suspect that it will also affect animals.
Thank you.
Well, thank you very much. So our next question, also from the chat, was, can you share the reference for the Mexico City data? And so this question was asked kind of early on, Rob.
Yeah, I put it in the
Oh, you did?
chat.
Okay.
I did see
Okay.
that. I It's just a paper that was, I just listed the paper.
Oh,
So,
okay, wonderful, wonderful. Thank you.
so it might have come up
Let's see
by
here.
the answer, but yeah.
Okay, is there any case study using the Saharan airborne transported to America? It's your next question.
We haven't played with that for this data set yet. Something we definitely want to look at. We have some imagery, I think, that might be on our Dark Target website, but we have not done any explicit quantitative looking at that yet.
Okay, well, thank you very
And
much.
that's again, desert dust coming off of Sahara and across the Atlantic and toward the US.
Yes, thank you very much. So the next question is, so you have AOD value at 2 times per day from MODIS and multiple from GEOS. Can you explain how the value at a given location or cell is estimated at a given time?
I think Jennifer, did she answer that in the chat? I can't remember. I thought she did. Jennifer Way. I know. If she didn't, I'll try and answer.
Yeah,
Okay,
can you?
Jennifer?
I think I trying to answer Sophie's question regarding how do we sort of merge all the level 2 from all the sensors into a level 3. So I sort of given a very generic. So we do put the constraint spatially and temporally within the specific grading system that Rob sort of alluded to earlier. And then we also consider the quality control with all the pixels that's sort of under different sensors. So once it passing all these constraints, and then with our level 3 right now, it's just sort of simple average. So we do not put any weighted sense
that's
favor
right,
any
exactly.
of the observation.
So right now, yeah, we weight everybody equally, thinking that everybody is just as good, each one. But at some point in the future, we hope to look at it in more detail and say, oh, well, this sensor on this view or this angle might be a better, might give us a better retrieval than that sensor at that angle on that condition, that kind of thing. So, but for right now, everything is equally based.
Okay, well, thank you very much, Jennifer, and also thank you, Rob. I mean, that's what makes it a little more challenging by asking the question in the chat, because the answer might not be directly associated with that, with that question, like concurrently in that one spot. So, okay, so the next question is, how near real time is this data, and is there a plan to include IFC data once available?
What kind of data? I didn't hear.
It says IFC data.
I'm not sure what that means, but in terms of real time, does anyone want to, my group want to say hello and answer that? And if not, I'll just bring it in. So this particular data set was intended to be kind of a demonstration in a way. So right now we're only doing 2019 to 2022. We have, I think we've gotten almost to the ability that we could produce it much quicker and through 2023 and 2024 into the future. But that's not what we produced here yet. So right now, yeah. So it's 4 years worth of data we've produced.
Well, thank you very much, Rob. Before I hop to the question and answer panel, another question was why? Oh, okay, I do see that there's a response to that one regarding the CDF versus HDF or HDF EOS data format. So why don't we go ahead? We're going to go ahead and jump directly to the Q&A here. It looks like some have been answered already, so let me scroll down here. Okay, I think Jennifer Way answered the level 3 versus level 2 data question and just repeated that now. So let's see here. And Virginia as well. All right. Okay, so let me take one more look up at the chat here. Okay, looks like the questions in the Q&A were answered. So I'm gonna need to.
You still here, I think.
So another one of the questions is, let's see, is the data available for aerosol type, dust, smoke, and sea salt?
So the answer is not directly, no. We're producing optical depth only. For the individual sensors, we have a parameter that's called fine mode fraction or fine mode weighting, which gives sort of a sense, especially over ocean, about the size of the particle, but it doesn't explicitly yet produce aerosol type. For that, we need other types of observations and measurements to do that.
Okay, well, thank you very much,
If
Rob.
anybody has to add more detail than that, or we can ask offline at some point.
All right, so the next question is, could you explain the difference between the products, the XAERDT level 2, MODIS Terra, and Mod 04 level 2?
Okay, I see Andrew. I don't know who Andrew is here, but it looks like Andrew tried to address some of that. So yeah, the idea is exactly right. So there's a standard
Oh, I see that,
product
yes.
from MODIS and VIIRS as well, which are again produced kind of almost operationally and in near, also in regular and all the way back to the beginning of the missions. And those, for example, in MODIS is called Mod 04 product. And then over VIIRS, it's been the short name. It's called XAERDT. And to differentiate our running of both MODIS and VIIRS with the geos here, but it's all a consistent data set together, we call it XAERDT. So the X for all different sensors and the air for aerosol dark target. So that's is that a good enough, or do you need more information?
So I do see a detailed response from Andrew up a bit. So if the participant has additional questions, please feel free to enter those into the chat. Okay, so the next question is, let me scroll up a little bit in the chat. How effective is the dark target in terms of PM 2.5?
Again, I haven't jumped in there. I'm just seeing if anybody else wants to answer from my group, or anyone else first who's more involved in PM.
What was the question again?
Like how good is AOD related to dark target in terms of PM 2.5?
That's an area of active research.
Mhm.
There's definitely a relationship between dark target AOD and PM 2.5, but it varies based on meteorology and a whole bunch of other things. But there's a lot of active research on that. There's a whole literature to look at to answer that question. Yeah.
So aerosol optical depth relates to the whole column, and it's the total aerosol regardless of what its size is. And then the PM 2.5 is particle matter less than 2.5 micrometers, and it's measured near the surface, so at nose level. So they're two different things, but they're often, they can, not often, but they can be correlated. In some places they can be very highly correlated depending on the place and time.
Okay, well, thank you very much to our Q&A panelists, science team Q&A panelists. Thank you also, Rob. And so the next question is, when could you produce retrievals from the flexible combined imager over Europe?
That's a fun question. Yeah. Well, assuming so the imager, I think they found a way to start producing data soon. So part of it depends on whether we have access to the data here, so that we can work with it. So that's one part. But yeah, theoretically, once we have data and we kind of know what the instrument's performance is and what, I mentioned things like wavelengths and wavelength shiftings and things like that. So once we know all that information, we can theoretically run retrievals.
Well, thank you.
Time and energy to do it.
Well, thank you again for
But it would be
that.
fun to do. And so hello, Taro. I think we can do this.
All right, well, wonderful. Thank you very much. And our next question, Robert, I don't know if you feel comfortable sharing your NASA email address, but if you do, if you could type that into the chat, that would be great. Let's see. Our next question is, why not use differential weighting based on proximity across space and time given differences in the spatial and temporal resolutions of multiple inputs to estimate AOD?
Rob, we can take a stab over
Yeah,
here.
you can. I see stuff popping up, so I was trying to read the question exactly. Yeah, go for it. Please do.
Um, we may, if this continues, if we have funding and we continue to work on this project, we might go to a weighted average, probably based as much on quality of the retrieval as it is on temporal and spatial distances.
Right. So, I mean, they're all, like we said, they're all about at the same time. So that's part of, at least the intention of the merge is everything within a half an hour of the same time period will go into one thing. So it's all real close. But what you have is, you have some sensors with a better, for example, you might have a better observation geometry, like one you might like if it's the observation is closer to being vertical, or what we call it nadir, or you might like it better if it's a wide, if it's at the edge where you have more information about the atmosphere. So it's kind of a tug, a push and pull. And it might depend on different regions, different areas. So part of what we're doing, and Yingxi and Virginia are very involved in this, is kind of trying to validate these products in many different ways. So I mentioned AeroNet as a surface parameter, as a surface kind of truth. But then we could look at each individual retrieval from each individual sensor, and at some point decide, hey, we like this one better, we like this one less better, that kind of thing. And so, but that takes a lot of work, and so you know we intend to do that, but it takes time.
Okay, well, thank you very much.
Yeah, I'm just reading the responses.
Okay, so the next question is, and we are now in the extended Q&A period,
Okay.
would the data still be accurately obtained if there is a drastic change in the climate or weather conditions?
This is my soapbox, Rob.
Okay, you go for it.
Because the dark target algorithm is physically based, it will be able to respond to changes in the climate and weather better than a machine learning algorithm would.
Okay, well, thank you very much, Lorraine. I am just checking through here. I do see, thank you so much, Andrew, for your very detailed responses regarding the differential weighting formula. I'm just scrolling back up through the chat to make sure I have not forgotten anybody. So bear with me. Thank you so much for your patience. Alrighty. So the next question, I don't know if anyone wants to tackle this. Is there a possibility for humans to execute some actions that will reduce aerosols?
Anybody want to go soapbox? Or the answer is, of course, yes, that people can do things to change some aerosols in terms of and actually the places like Eastern U.S. and such, the U.S. and parts of Europe have done actually quite a good job at reducing overall aerosols, at least from certain things like pollution, like industrial pollution and auto exhaust and things like that. Unfortunately, there's an equal or maybe greater than amount of increased aerosols from wildfires, and depending on where you are, it might be some dust. Desert dust may be decreasing or increasing. So it's kind of a mixed bag. So that would be my answer so far. But others may have a more detailed answer to that question in terms of humans being able to change aerosols.
All right. Anybody? Thank you very much for your response. Let me just hop back to the Q&A
Mm-hmm.
and see if we have any new questions at this point. Quite a few had been answered by our Q&A panelists. Thanks for your patience. I'm just looking through. I think at this point,
Do you want
Adore?
me to add my email here for questions, or you can share them?
sure,
Or how does
sure.
it-
So
I mean,
yeah, so
I mean,
just as a, sure. So
I don't.
just really quickly for everybody. So there were a couple of questions that as host I can provide a response to. Number one, there were several questions regarding whether or not today's event is being recorded. Yes, today's event is being recorded, and we post all of our NASA Earthdata data discovery and data access webinars on our Earthdata YouTube channel, as well as on the Earthdata website, which you can find at earthdata.nasa.gov. And you're going to click on Learn, and you will see an option for webinars and tutorials. For YouTube, it is, if you search NASA Earthdata on YouTube, and I can put the link in the chat, you should find, gosh, I think we've got over 400, science team workshops and shorter data recipes and tutorials and, hour-long data discovery and access webinars across the earth science disciplines on there as well. And then the second question, which is a very popular question, we currently do not offer a certificate of completion for our NASA Earthdata webinar series. That being said, we are looking into offering a certificate of completion in the future. So that might not be the most popular response, and I can certainly appreciate how valuable that can be, a certificate of completion. Let's see if I see anything else. What we will do, if there are no further questions, we will leave the virtual meeting space open an additional 10 minutes from end time, and I will leave the polls opened as well for that time period. If anybody thinks of something that you'd like to ask our speakers or science team Q&A panelists, please feel free to, we do have a question, to jot those into the chat or the Q&A. And I will forward these logs to our speakers so that they can follow up with you offline. But we do have one more question. In the retrieval algorithm, what optical property model did you use to do the retrievals?
So I'm on mute.
So again, the question is, in the retrieval algorithm, what optical property
What's up, Emma?
model did you use to do the retrievals?
So we have a bunch of so we have some fixed optical property models. We have we do actually do it two different ways. Without getting too much detail, for retrievals over ocean, we feel like we have a little bit more multispectral information to work with. And so we actually have choices of models. And essentially some are more fine size particles, so smaller particles, and then we have some that are larger particles. And then we use the retrieval to mix them together to produce kind of a best fit. And so over ocean, we have that information. Over land, the models chosen are a little bit, they're more fixed based on climatologies. And so we have models for example, a model for urban industrial pollution, and that's kind of fixed by location. And we have a model for more like highly absorbing, blacker looking smoke, and that's sort of fixed by location. And any one of these overland models can be mixed with dust. So that's basically how the retrieval works. And so those optical are pretty much based on literature and climatologies of ground-based measurements from AirNet. And hopefully that made sense. And we can ask more questions afterward. We can provide with more details in terms of the aerosol models, yeah.
Okay, thanks, Rob.
Yeah, so
so-
and then there's links
sorry.
to our website and such. So you can put it here. I'll put it here. That's our website, and there'll be some more information about the models chosen there.
Yes, I typed the website and the paper.
Okay, oh, perfect.
Yeah.
Except that's not the correct paper. I'll get it right.
Well, thank you very much, everybody.
Thank you.
All right, let me just do one more quick scan. And if there are no further questions, I'd like to thank our speakers for this afternoon, Tasia and Rob Levy, Tasia Owen, and then also the science team Q&A panelists who have joined us to respond to our questions here. Let me look one more time. Just scanning through the chat. I see a response. Let me look through the Q&A. I think we have tackled all of the questions. So I really appreciate not only the speakers, but also all of our participants for joining us this afternoon. And I did put a little bit of information for our next webinar, which will be held on June 26th, and will focus in on the Delta X mission campaign data sets and data discovery and data access. So thanks very much. With that, we will log off from the audio component and leave the virtual meeting space open an additional 10 minutes. All right, well, thanks everybody. We appreciate you. Have a good afternoon
you.
or
Thank you.
evening. All right, or morning. Goodbye.